Hello and welcome to my talk. My name is Debmalia Panigrahi. I am from Duke University. This is joint work with Anupam Gupta from CMU and Amit Kumar from IIT Delhi. I'm going to be talking about a caching problem. It's called caching with time windows. So let's start off by defining the generic caching problem. So imagine that you have a disk. Think of this as a slow device, but it can hold a lot of pages. In fact, it can hold all the n pages that we are interested in. And there's a fast cache, but the cache has the restriction that it can only hold k pages. And think of k as being much smaller than n. Now, the individual programs issue page requests. They send these page requests online to the cache one at a time. And these requests have to be satisfied by the cache by bringing the corresponding page into the cache. The question, if the page is already there in the cache, if a requested page is already in the cache, then you don't need to do anything. But if the page is not in the cache, then it has to be fetched from the disk. And to make space for that page, you have to evict an existing page from the cache. The goal of caching is to design a policy that minimizes the number of cache misses, or in other words, the number of times that you evict a page from the cache. And in the weighted caching problem, every page also has a weight. And the goal now is not to minimize just the number of cache misses, but the sum of weights of all the evicted pages across the entire sequence of requests. So this is a classic problem, and it has been studied from the perspective of competitive ratio, which is defined as the ratio of the objective of the online algorithm to the objective in an optimal solution. And it's well known that both for the weighted and the unweighted versions of these problems, the best deterministic algorithms obtain a competitive ratio of k or theta of k, whereas the best randomized algorithms obtain a competitive ratio of theta of log k. So this problem is essentially solved from the perspective of competitive ratio. In this paper, we are looking at a generalization of this problem that we call caching with time windows. The idea here is that when a page request arrives, it does not need to be served immediately, but every page request also has a deadline in the future, and it must be served before that deadline. In other words, if I get a request R for some page P at time T with a deadline T prime, then page P must be in the cache at some point in the interval between T and T prime. It does not need to be in the cache precisely at T, but it needs to be in the cache at some point during this interval. Now, the way that this changes the caching problem is that it allows us to reorder the servicing of requests. So for example, here I have shown 4 requests for 2 pages that are interleaved. So the requests for P1 and P2 arrive alternately. Now, in a classic setting where all the page requests must be served immediately, and I have only a single slot in my cache, I need to keep slotting in the requested page and therefore will suffer a cache miss on each individual page or on each individual request. But if I have these longer time windows to satisfy my requests, then all I need to do is need to do is serve both requests for page P1 together, as I have shown, at time t, and then serve both requests for P2 together at a later time t prime. And by doing this, I am basically reordering the order of reordering the two requests in the middle, the second and the third request. And by doing that, I am saving on the number of cache misses that I suffer. So this problem has several motivations. From a theoretical standpoint, it has connections to various online problems that have been considered in the past, in particular a problem called reordering buffer management. But also, uh, it is part of this developing literature on online algorithms with delays or deadlines. in the last few years, several online problems have been considered in a model where requests don't need to be served immediately, but can be served within a given deadline in the future. And our problem also falls in that category. In particular, this is precisely the standard caching problem in the setting of the deadlines. Now, from a practical standpoint, uh, there are situations where caching with time windows is very relevant. For example, in the Linux kernel, there's a scheduler called the deadline IO scheduler, which precisely does what we just described. So you get page requests, but these requests can be served in the future. Also, in video on demand streaming services, pages are cached, or segments of videos are cached over time. And there is this question of how do we reorder these segments in a manner that optimizes service. So in terms of previous results for this problem, it is known that the problem admits a deterministic algorithm that has a competitive ratio of O of k, which of course is the best you can do because this clearly generalizes the standard caching problem. In the world of randomized algorithms, it is known that the unweighted caching problem with time windows has a log k competitive algorithm. But what was an open question before our work is whether you can also obtain the same competitive ratio for the weighted caching problem with time windows. So we don't quite completely resolve that problem. That problem remains open, but we get an exponential improvement in the sense that we obtain an algorithm that has a competitive ratio of log k times log n. So there's this additional factor of log n, and I'll say a little bit towards the end about whether this is necessary or how one might be able to overcome this. Additionally, we also studied the offline version of this problem. And interestingly, unlike the standard caching problem, either for weighted or unweighted settings, this problem is NP-hard. So standard caching has simple polynomial time algorithms offline, but this problem turns out to be NP-hard. And in fact, it's also APX-hard. And we also give a constant approximation offline for this problem. So in terms of our technical contributions, our main contribution is a new LP formulation for the problem. So if you think of standard weighted caching, then the classic method of solving standard weighted caching is via solving an LP online. But this natural LP for weighted caching does not quite generalize to weighted caching with time windows. In particular, it has an integrality gap of omega k. So our main contribution from a technical perspective is to avoid this integrality gap by introducing a new LP formulation for caching-like problems, a new LP framework for these problems that we call the hitting set framework. And in fact, to the best of our knowledge, this is the first LP-based techniques for any online algorithm in this new model, this emerging model of delays or deadlines. So let's dive straight into the LP. And let's start off with the standard LP for weighted caching. This we will call this the interval covering LP. The reason is this LP looks at every page, looks at all the requests for this page over time, splits up the timeline according to these requests into intervals, and then simply records whether the page is evicted in each of these intervals or not. So for every interval, you have a variable which records whether the page gets evicted in the interval, as I've shown in this figure. And that's sufficient because pages being brought into the cache is basically on demand. So if you have a request and you don't have the page in the cache, then it must be brought into the cache. So you don't actually need to explicitly record the insertion of pages in the cache in the LP. All you need to do is to record evictions. And this is very useful because this allows us to express the constraint that the cache can only hold k pages at a time in terms of a covering constraint, as we will see later, because covering constraints are things that we can handle online. So unfortunately, in our case, we can't quite do that. So on the left, I have shown the standard LP for weighted caching. I'm not going to describe this in detail, but it basically does what I just said. In our case, however, since we have time windows, we need to have closer control over when page insertions happen. So page insertions are no longer on demand. I give, for every request gives an entire interval, and the corresponding page might be inserted in the cache at any time during this interval. So we can't get away by not modeling page insertions at all. On the other hand, if you want to do an explicit modeling of page insertions, that turns out to be difficult for precisely the reason that I mentioned in the previous slide, because if we have explicit variables for insertions, then those variables need to satisfy packing constraints to ensure that the cache does not contain more than k pages at a time. And packing constraints, we don't really know how to handle such packing constraints in an online algorithm. So how do we get around this problem? So I'll skip this slide. So to get around this problem, we design what we call a hitting set IP relaxation. So let's for a second go back to the standard caching problem. And let's think of the following kind of constraint. Let's fix a time t and look at the last request for every page before this time. So this last request for every page defines an interval from the request to the current time. And I claim that in at least n minus k of these intervals, I must have evictions. Because if I don't, then I have more than k pages in the cache. So that's precisely the constraint that one writes in the standard LP. But now I can generalize this constraint a little. So there was no real reason for choosing the last request for every page. I can choose any request for each page. So for every page, I select any request, and I can enforce exactly the same constraint. Of course, in the case of standard caching, these constraints are no stronger than just using the last request. But since we have explicit intervals in our case, it helps to generalize the constraints to using any request. So at this point, I take all pages. For every page, I choose any request. I define these intervals going from the request to the current time t. And over these n intervals, I claim that I must have at least n minus k evictions. Now, one other fix that we need to do is if an interval for a request in our case stretches beyond the current time t, then we can't say that the eviction happens before the end of the interval. So we have to stretch our interval also all the way to t. Okay. So we call this extension of the interval the right extension. So the interval either gets stretched to the current time t, or it gets stretched all the way to the right to the end of the interval. So over the right extensions, we write a constraint that looks very similar to the interval covering constraints that we talked about earlier. Now in standard paging, a crucial fact is that in writing these constraints that we just described, we don't need to include the currently requested page. We can claim that among the n-1 pages excluding the currently requested page, at least n-k must have been evicted, because only k-1 pages other than the currently requested page can reside in the cache at the current time. Now that becomes very tricky in the case of time windows, because even if I have a current request, I do not know when this request is going to be served. So insisting that this request be served now is too strong. That will rule out feasible solutions. So we cannot remove the currently requested page or any currently requested page from the constraint that we write. And this makes the LP weak. So to strengthen the LP, we introduce a new set of constraints. So to understand this constraint, let's fix a request. Let's say an interval I that goes from S sub I to E sub I. Now take any other page, let's say a page P prime, and choose any interval that ends before E sub I. Okay, so here I've chosen some interval S sub I prime to E sub I prime, and I've shown two different possible cases. Now what we do is we extend these other intervals, the S sub I prime to E sub I prime, we extend these possibly in both directions to match the two ends S sub I and E sub I. So as you see in this figure, in one case, I didn't need to extend it in both directions. In the other case, I did need to extend it in both directions. But once I make this extension, then I can claim that excluding the page that corresponds to interval I, for every other page, all the n-1 other pages, if I take one such interval and do this extension, then out of those n-1 pages, at least n-k pages have the following property. You must have either inserted the page or evicted the page. So you must have at least touched the page in the extended intervals. Because if you didn't even touch the page in the extended intervals, then the page must have been resident in the cache throughout SI to EI. And if that happened, then you cannot be served. If that happens for more than k-1 pages, that means you cannot service the SI-EI request. So we get we get this constraint that says something about all pages except a fixed page for which the constraint is being written. So in some sense, this constraint gives me back some of the power that I had in standard caching, where I could remove a page and write my constraint. So those are the two sets of constraints that we write. Those are covering constraints as we wanted. I won't go into the detail of exactly how this LP is set up and what the variables are, but let's go into how the algorithm proceeds with this LP. So the algorithm has 3 steps. We have to obtain a fractional solution to this LP. We have to round this solution to an integer solution. And eventually we have to turn this integer solution to the LP to an actual cache schedule. And we have to do all of these online. So the first 2 steps are somewhat similar to standard weighted paging with some caveats. First, we have an exponential number of constraints. Remember that we chose any one request for each page. So that creates a very large number of constraints, and we need to be able to handle that. Second, we have 2 types of constraints. We have constraints for write extensions and double extensions, and that creates some complications. And finally, our decision variables are for pages at fixed times rather than over intervals. So remember, in the interval covering version, for each interval, we simply recorded whether the page got evicted during the interval or not. But here we have to actually design decision variables that tell us whether a page is touched, whether inserted or evicted at a given time. We can't work with intervals because I can have a lot of overlapping intervals for the same page at any given time. So that also creates some complications, that we don't have decision variables over intervals, but rather have them over pages and times. But the more interesting part, or the more novel part of what we do, is in converting this integer solution into a cache schedule. And this, at a high level, has 2 main challenges. The first is that we are not able to separate evictions and insertions. So remember that so in the double extensions, we couldn't really say whether a page would be brought in to the cache or taken out of the cache in the double extended interval, but we could say that one of the 2 would happen. So we are recording both evictions and insertions, and we have no way of distinguishing the 2. Moreover, we do not record all, or the LP does not record all evictions and insertions. So for example, if you used our framework for a standard paging problem, then you would only get the evictions from the LP. So we can't separate between evictions and insertions, and we don't know all of them either. So not all the insertions and evictions aren't recorded. So these are the two challenges that we must overcome in our algorithm. So going a little further, so here's the main idea. So imagine that you have a lot of light pages and one very heavy page that keeps getting requested very often. So then when I evict, I want to evict the heavy page just once. I don't want to pay this cost many times. But when I evict the heavy page, I want to serve all my light pages because I have created this hole in the cache that I want to exploit. On the other hand, there is some merit to not serving a page before its deadline has arrived, because in that case, I am losing the opportunity of piggybacking on another service of the same page because there's a new interval that might come in the future. So there are these two competing goals that I want to piggyback as much as possible with heavy evictions. On the other hand, I want to postpone service as much as possible so that I can batch process the service requests for the same page. And the main challenge in the algorithm is to balance these two competing goals, and that's what we show we are able to do. So in the offline case, this is rather easy. What you could do is you can make decisions based on the information you have at some point, but you can go back in the future if you realize that there was an opportunity to batch process that you missed out, then you can go back and change the decision that you had made in the past. So in the offline case, we use a step that's somewhat reminiscent of the standard reverse delete step to implement this idea. In the online case, we clearly can't go back in time. So here we have to do a much more careful balancing between waiting long enough and waiting too long. And we do this using a tree structure of request intervals that's somewhat morally similar to an algorithm of Azar et al. For the online service with delay problem. So that's all I have in terms of technical details. Please read the paper if you're interested. I want to conclude with a couple of comments. First, our techniques actually generalize to arbitrary delay penalties. So what do delay penalties mean? So when a request arrives, we no longer get a deadline, but we actually get a monotone function which maps the delay in serving the request to the penalty that it results in the objective. So this, of course, is more general than deadlines. You can simply model deadlines as having a penalty of 0 until the deadline, and then having infinite penalty subsequently after the deadline. So our algorithm with some additional ideas extends to this case. Now what's open, as I said earlier, is to get a log k competitive online algorithm for this problem. Remember, our competitive ratio is log k times log n. But interestingly, we are not able to show any gaps for our algorithm or our linear program for that matter that's any worse than log k. So it's very possible that our algorithm itself, or at least this linear program, will eventually give the tight log k bound. It's just that our analysis at the moment cannot handle, has this additional factor of log n creeping in. That's all I have. Thank you, and I look forward to your questions.